An online store records every order in its live database, brilliant at handling one order at a time, quickly and safely. Then a manager asks a very different question. Run that on the live database and you'd scan millions of rows while customers try to check out. It would crawl. So companies build a separate copy, tuned for exactly this kind of question, a data warehouses. To workloads, opposite goals. On the left, the operational system OLTP. Its whole life is small writes, so it's normalized, data split across many tables, so nothing is stored twice. On the right, the warehouse OLAP. The opposite. A few enormous reads that sum and average across years. And to make them fly, it does what the textbook warns against. It deliberately denormalizes. Inside that warehouse, the data takes one of two shapes, the star schema and the snowflake. Those two layouts and the trade-off between them are what this lesson is about. A warehouse holds two kinds of table, and telling them apart is the whole game. Let's meet both. First, the fact table. Its rows are events, a sale, a shipment. Every row carries just two things. Measures, the numbers you'll add up, like amount and quantity. And foreign keys, pointers out to the descriptive tables. Keys and numbers, nothing else. Long and narrow. And it can hold billions of rows. Second, the dimension tables. These carry the descriptive context. The who, what, when, where. Product holds name, category, brand. Date holds day, month, quarter, year. Wide, full of words, and relatively small. Every foreign key in the fact points into one of these. Hold that contrast in your head. Fact tables are numbers you aggregate, plus keys. Dimension tables are descriptive text you filter and group by. Numbers in the middle, words around the edge. Now put them together. Fact table dead center, dimensions radiating out around it, each joined by a single line. Watch the shape that appears. Here's the fact table in the middle. Sales, keyed to four dimensions, carrying its two measures, amount and quantity. The date dimension joins on the date key. That's when the sale happened. The product dimension joins on the product key. What was sold, its category and brand. The store dimension joins on the store key, where the sale happened, the city and state. And the customer dimension joins on the customer key, who bought it. And there it is, fact table at the center, dimensions as the points around it. It looks like a star, and that's what we call it. Notice each dimension is a single wide table. The category sits right inside product, the state right inside store. Nothing branches further out. That flatness is deliberate. Before you build any of this, answer one question first. The question people skip. What does a single row of the fact table actually mean? That's called the grain. Here, we'll say the grain is one line item on one sales receipt. Fix that first, because your measures have to match it. If a row is one line item, then amount is that line's amount. Mixing grains, a per receipt total next to a per line quantity, quietly corrupts every number you compute. One quick distinction on those measures. Most, like amount and quantity, are additive. You can sum them across any dimension. But a few are non-additive, like a margin percentage. Summing those gives nonsense, so you average them instead. Now the contrast. The snowflake keeps the same central fact table, but normalizes the dimensions. Instead of one flat white table, each dimension splits into smaller related tables. Let's snowflake product and watch. In the star, product held everything in one table. The name, and right beside it, the category and brand. Plain text, repeated on every product row. In the snowflake, product keeps only a category ID and a brand ID, foreign keys. The category name moves out into its own category table. The brand name into a brand table. The dimension has fanned out into subdimensions. Do that to every dimension and the arms of the star split again and again, until the picture looks less like a star and more like a snowflake. Same data, more tables. And the category name is now stored exactly once. In category, not copied onto every product. So which do you pick? A genuine trade-off. And it comes down to one tension: redundancy versus joins. The star wins on speed. Each dimension is one flat table. So a query joins the fact to each dimension just once. Fewer joins, faster reads. The cost is redundancy. The same category name is written on thousands of rows, taking more storage. The snowflake wins on tidiness. Each description lives in exactly one place. Far less redundancy, cleaner structure. The cost is joins. To read a category name, you now hop fact, then product, then category. So which wins? Usually the star. In analytics, read speed beats a bit of saved storage, so we cheerfully denormalize, accepting redundancy to cut joins. The mirror image of an operational database, which normalizes to protect its rights. Different job, opposite choice. Let's see the star earn its keep. The question a warehouse exists to answer: total sales by product category, by month. Watch how the star answers it. We start from the fact table, sales, and join it to date on the date key and to product on the product key, one clean join each. Then we group by month and category and sum the amount. Notice the shape. The number we add, amount, comes from the fact table in the middle. The words we group by, category, month, come from the dimensions around the edge. That's the star pattern in one query. Aggregate the facts, sliced by the dimensions. Let's make that concrete. Same question, both schemas. Total sales for electronics in Mumbai stores. We'll count the joins each needs, then compute the answer. Here's a little sample data, 3 sales rows and the lookups. Products 10 and 11 are electronics. 12 is furniture. Store 3 is Mumbai. Store 4 is Delhi. Take the star first. Category sits inside product. City sits inside store. So we join sales to product and sales to store. One join each. Two joins. Apply the filters. Row 1 is electronics and Mumbai. Keep. Row 2 is furniture. Drop. Row 3, electronics and Mumbai. Keep. Sum the survivors. 5,000 plus 2,500 is 7,500. Now the snowflake, category and city have moved out into their own tables. So to reach the category, we join sales to product, then product to category. To reach the city, sales to store, then store to city. 4 joins, double the star. But here's the point. The chosen rows are still 1 and 3, and the answer is still 7,500, identical. The only difference is the work. 2 joins versus 4. That's the whole trade-off in one example. Now a number on the redundancy. 10,000 products, 50 categories, 1 category each. Count how many category names each schema physically stores. In the star, the category name lives inside every product row. 10,000 products, 1 each. 10,000 names stored. Electronics written out thousands of times. In the snowflake, the product row holds only a category ID. The name lives once. In category, 50 categories, 50 stored names. The difference is stark. 10,000 minus 50 ite me 9,950 fewer repeated strings for one column alone. Multiply that across every descriptive attribute, and you see why snowflaking reduces redundancy. The star accepts it, trading storage for saved joins. Your turn. Here's a sales fact table carrying amount and quantity. Here's the question. If you wanted the product name in your report, is product name a measure that belongs in this fact table or a dimension attribute that belongs somewhere else? Pause and decide before I answer. Here's the answer. Product name is a dimension attribute. Ask the test. Would you ever add up product names? Of course not. There's no sum of names. It's descriptive text, the what of the sale, and it belongs in the product dimension reached through the product key. The fact table keeps only what you aggregate, amount and quantity, plus foreign keys. Put the name there, and you'd repeat that string on every single sale, blowing up the biggest table in the warehouse. If you said dimension attribute, you've understood the heart of this lesson. Trap 1. Assuming normalized is always better. It is, for a system protecting its rights. But a warehouse optimizes reads, where the denormalized star often runs faster. Right rule, wrong workload. Trap 2. Putting descriptive text in the fact table. Names, categories, cities are dimension attributes. The fact holds numbers and foreign keys, nothing more. Measures plus several foreign keys, almost always your fact table. Trap 3. Thinking the star removes redundancy. It doesn't, it removes joins. The redundancy still sits inside those white dimensions by design. It's the snowflake that removes redundancy by normalizing. And trap 4. Writing of the snowflake as too slow. It adds joins true, but modern engines handle several fine. It's a trade-off between read speed and clean storage, not a rule that one is always wrong. Let's lock it in. A data warehouse serves analytics, OLAP, kept separate from the operational OLTP system, holding history so you can compare across years. Its tables split in two. Fact tables hold the measures you aggregate plus foreign keys in the center. Dimension tables hold the descriptive context, who, what, when, where, around the edge. The star keeps dimensions flat and denormalized. Fewer joins, faster reads, at the price of repeated descriptions. Usually, the choice. The snowflake normalizes those dimensions. Less redundancy at the price of more joins. Decide the grain first, keep facts and dimensions straight, and you can read or design any warehouse schema with confidence.